So we will be looking at the delta potential well, namely two different states. The bound state, where the energy of a particle is less than the potential energy, as the potential energy goes to positive infinity and negative infinity in the x direction, which we will show in a little bit, and the scattering state, where the energy of the particle is greater than the potential energy. Um, Now the delta function well, delta potential well looks like this. It has the form of v of x equals negative alpha times the delta function. Now what this delta function is simply, we'll just call that x. It's defined as 0 if x is not 0, and infinity if x equals 0. So what does that mean? That just means that we have a spike. In our case, it's a sort of spike like this that goes to infinity. The negative spike is because of this negative alpha, which is just a constant. It's called a string factor. Uh, if you plug the solution in later, you'll see what this alpha actually does, but we'll get there. Um, but yeah, and another property of this delta function that's also important to note, by the way, this is v of x, and this is x. So what it is here it's infinite, and everywhere else is 0. You can think of this as a sort of a mini potential, infinite potential box. Um, but here the potentials are 0, and it's only a small spike over here. But also another point I want to make about the delta function is that the delta function has this property where if we integrated, and if the point that makes the argument of the delta function 0 is within the points of the integral, this thing equals to it just equals 1. This is an important point. In this case, imagine this, right, is just the same thing as if I wrote x minus 0, right? So we have the spike at 0. If I had a spike at another point, I could just generalize it to x minus a, right? Um, and say that if the a is within these bounds, then the integral over dx equals 1. But yeah, so another property is that when multiplied by some function, some arbitrary function, by the delta function, right, over negative infinity to infinity, if again this a is within negative infinity infinity, which it is because negative infinity and infinity cover the whole plane, right? This is just going to be f of a. So you can just think of this delta function picks out uh, whatever makes the argument 0. The argument is x minus a. So what x makes the argument 0? A, right? So this is the a. So f of a. So this is you get this. This is a general property. Um, Another thing we can talk about um, the delta function is that it essentially it's going to help us resolve the discontinuity that we will see. So I mean, let's just start by doing the solution. So first we will be looking at the state E that is smaller than 0. So we will be looking at a bound state. Let's write down the Schrodinger equation. I will first write down the generalized Schrodinger equation. Right, so this should be plus. This is the potential. Now let us write down the Schrodinger equation with our potential. where the potential is simply alpha times delta x, or the delta function. This is the Schrodinger equation. Um, so what we need is to look at different regions. So let us say this is going to be region 1 and region 2, because our function will spike at 0. Let me do that better. Our function will spike at 0. And so we will be looking at where x is smaller than 0 and where x is greater than 0. So where x is smaller than 0 and x is greater than 0, this will just help us with some boundary conditions, namely the fact that, not boundary conditions, but the property of a wave function that it should not blow up. The wave function can't just go on continuously. So what we will see is that when we take a limit as x goes to infinity or negative infinity, some terms cancel out in the solution. So let's just write down. So this is simply the first part of the Schrodinger equation. Now, since we are going to look at x smaller than 0 first, right? So this section pretty much, right? We know that the potential here is 0 because this is simply a spike. Let me draw that better so you guys know that this is a spike simply localized right here. So it's only at one point it takes a value of infinity, right? That's how the delta function is defined, right? At 0, if it's 0 if x is not 0, and it's infinite if x is 0. So only at 0 it takes an infinity value. Everywhere else, here and here, we simply have a v equals 0, right? So since we're looking to the left of here of the spike, we see the v equals 0, and then this equals to e psi. So let us just do a little bit of rearranging, right? Just bring that constant terms over to the right side. We can write this as e psi to make it easier. What we will do is we will simply define this term. So we will define this term as k equals negative 2me over h bar. Now, why do we put the negative inside the root? That seems unphysical. There shouldn't be a negative inside the root. Well, the reason is because we already say that e must be less than 0. So e is negative. This negative and this negative cancel each other out, so the root is positive. So this actually works out, right? If it was positive e, right, which we will look at later, an e that is positive will mean that we just don't include this, right? So it'll be like instead of it being this, right? So let's write down the k here. Forgot the square, sorry. We will have k squared psi. In the case of the in the case where e is greater than 0, right? Where this is a positive, we will leave this out, and it would be negative k squared. And in that case, we get exponential solutions with I in them, right? But in this case, right, the solutions of these are simply a e to the kx plus b e to the kx. Now, if you want to solve these, actually, there are a number of ways you can do these. You can just search up um, or look at a book for differential equations. A good way to do them, which I won't do, but I'll give you as an exercise, um, is to do something right in this fashion, and then pretty much um, pretty much do separation of variables right on this, and then do a separation of variables on this, and you will get two different answers. So this is negative, but you will get the logarithm, like you get d psi over psi, right, which is like ln of psi, and then you must take the e to the, so you get psi equals e to the something. This works out. If you want to try this for each one, this will work out, but this is the general solution. So this is for x that is smaller than 0. For x that is greater than 0, we do the same thing. If we actually get the same exact solution, we're just going to have to change these constants because, well, yeah, it's for the x that is positive. So we can just choose c e to the kx plus d e to the negative kx. Okay, so this is the first region, right? And this is the second region. So if we look at this, we have two different or two similar solutions with different constants for each region. What we will do now is perform some, apply some boundary conditions, right? So we know that the wave function cannot blow up. The wave function must come down, right? So we know that as for since this is defined for x that is less than 0, we will take a limit as x goes to negative infinity. Oops. Let me just write this like this. And b e to the negative k times negative infinity. In this case, right, uh, this e to the negative k infinity can be written as a e to the k infinity, which just equals 0. Um, right? Um, but this b is simply going to be b e to the k infinity, which blows up to infinity. So what we must do is just say that b must be 0. So for our first region, right, x equals 0, so we will have a e to the kx. And then similarly, for the other region, we will take as x goes to positive infinity, because x is defined at values greater than 0. And we will get c e to the positive infinity, right, some constant times positive infinity, d e to the negative k infinity. Again, the negative one goes to 0, and we are left with c e to the k infinity going to infinity. So this goes to infinity. We can't have that, so we take c2 equals 0. And so we are left with psi 2 of x equal d e to the negative kx. So we have two different solutions, right? I can box them right here. I have two different solutions that look like this. Another thing that we must take into account is that at the potential, where the potential spike happens with the boundary, this thing, right, it's x equals 0, these wave functions that are defined here, they can do some wild things here, right? They can do these things, I don't know. They can go up and they can go down, do stuff like this, and then this one can go, do stuff like this. But right here at x equals 0, they must be the same value, right? They must be continuous at the boundary. So we do psi of 1, 0 equals a e to the 0 must equal psi of 2, 0, which equals b e to the 0. So we just say a equals b because e to the 0 and e to the 0 are 1. So since a equals b, we can simply write this as a sort of a piecewise function, right? So we can say psi of x equals, right, something like this, where b e to the kx, x is smaller than 0, and b e to the negative kx, x is greater than 0. And we can put the equal sign because they are continuous, right? They're defined at 0. So this is what we have, and we could equivalently just choose a. I just chose b. It doesn't really matter. Um, but yeah. So the second boundary condition, the one that's a little more hard to understand, is that the first derivative must be continuous. So what does that mean? If we have the spike at x equals 0, if we choose some minus epsilon and plus epsilon, which are just infinitesimal lengths from deviating from 0, and we take the limit that these infinitesimal lengths go to 0, right? So we just sort of like squeeze it. Um, we want to say that they will both um, come to be defined, right? So how do we show that? The way we show that is we need to find the d psi dx. And how do we do that? Well, if we integrate the Schrodinger equation, which is a second order differential, right? It's a second order differential right here. We will actually get um, what we want. We will get the d psi dx. So we will just apply this boundary condition, which is just simply integrated from negative epsilon to positive epsilon. Right. Let me bring this down over here. Plus positive epsilon of the v of x psi of x dx equals e, which is a constant, from negative epsilon to positive epsilon of psi of x dx. So the first thing we must see is that this whole thing is 0. Why is it 0? Well, because you have a finite value. You have psi of x that has some very small, right? Whereas a infinitesimally small length, right? And it has some finite height, right? So like let's take a um, sliver like a rectangle like this, and this rectangle is very thin. Let me um, let me make that a little bigger. This rectangle is like super thin. I can even give it some value like 0.0001, and then it has a finite value of like, let's say, I don't know, 5, right? If I want to find the area of this sliver, right, this is what I'm doing. I'm integrating, right? 5 times this number, I'm not even gonna do it, but 5 times this number is a super small number, right? It's infinitesimal. It's 0. It's gonna be it's 10 to the negative something, right? So that's sort of the idea here, is that you're sort of squeezing it to a very small length with a finite height. So it's just going to be 0. So what we get is that from negative epsilon to epsilon equals, and then at this point, we can simply input our um, potential, and our potential is, let me also bring these constants over, right? So we have the negative, in this case we don't, but um, right, because we just subtract this and then this negative cancel out, but we also have a negative alpha delta x psi x dx. So this negative, we can simply just take it out here along with the alpha, because the alpha is a constant. So all we're really dealing with is the delta function times psi x. So the delta function, the argument here, is 0, right? What makes the delta argument 0, right? X equals 0, right? So, and that is within negative epsilon on epsilon, right? 0 is included within negative epsilon on epsilon. That's how it's because these are just small perturbations. Um, so what we say is We haven't done this integral yet, but this is super elementary. We will see h bar squared. So we know from a property of a delta function that it simply picks out the value of its argument. That makes it 0, so psi of 0, that's it, right? Psi of 0, and then that's 1 from the delta x dx is 1. So it's simply just psi of 0. So, and then this is simply d psi dx, the integral of a second order differential is just the first order differential. So you just get d psi dx uh, evaluated at epsilon minus evaluated at negative epsilon. So that's simply, we can call that delta d psi dx equals this stuff. Right? And this is simply all it is. Now we must find the what d psi dx actually is. Right? So we must find for d psi dx for x smaller than 0 and d psi dx for x greater than 0, right? And then we simply find the difference, right, delta. So d psi dx equals, for smaller than 0, for x smaller than 0, we will do d psi dx. So it's bk e to the kx, right? Bk e to the kx, that's all d psi dx is. And then let us do the same thing for the other one. Let me just see this. Um, and then for x greater than 0, we get the negative kx, right? Bk, so there's a negative over here. So if we are looking at this, we simply take x equals 0, because that's where that's what we want to see if the wave function, right? Because the wave function looks like something like this. If the wave function is gonna be ordinarily continuous. So let us just look at, so I mean, e to the k0 is just 1, e to the negative k0 is just 1, and then let's look at the difference, right? Which just simply equals negative 2 bk. So just using this equation, by the way, you can do this for e greater than 0 as well. You just simply use this equation. It's just you're gonna have um, a different conditions for different boundary conditions. And your solutions are of course going to look differently as well. But we have negative 2 bk equals negative 2 m alpha over h bar squared. And then the psi of 0 simply means the wave function evaluated at x equals 0. So let's look at our wave function evaluated at x equals 0. We simply get b, right? No matter which one we do, we just get b. So this is just times b. Oops. So b. So let's just cancel some stuff out. This stuff cancels out, negative sign cancels out, b cancels out. So we're just left with k equals m alpha over h bar squared. Right, this is k. We also know that k we defined as negative 2me over h bar, which equals m alpha over h bar squared. Right, this whole thing in the parentheses is k. That's how we define k. If we just square both sides, right, to get rid of the square root, we get negative 2me over h bar squared equals m squared alpha squared, right, and h bar to the fourth, right, because this is already squared. Now if we just solve for e, right, let's cancel this, if we multiply h bar squared, right, this cancels. We're left with a square here. So what we are left with is E equals m alpha squared over, this is negative here, 2h bar squared. That is E. And you can see that there's only a single bound state. There's only a single energy, allowed energy. There is no n, like for example in the infinite square wall, where we can input different n and get different energies for each state. In this case, uh, the only thing is the alpha, the strength factor, um, which is pretty much how fast does the wave function uh, go to zero. That like that's all that is. Um, so we can look at the wave function solution again, and we can normalize it. So let's just write the wave function in this way. This is the way I would write a wave function, so as to include both positive and negative, right? So I'm just pretty much taking this whole thing and just writing it this way. You're allowed to do this. And let me normalize it now. So normalization is from negative infinity to infinity psi of x squared dx, which in my case equals, well, what I can do is, because I'm gonna have e to the negative 2kx. To make it easier for me, I'm just gonna divide this integral. So I'm just gonna say 2, because it's a symmetric along the x-axis. I can simply say 2 times 0 to infinity, right? Because it's the same exact thing. Like if I integrate, this is how the wave function looks. I can simply just integrate this part and then multiply by 2 because it's symmetric. This and this are the same thing, right? So I'll just do that. And so if I squared my wave function here, what I get is b squared, right? Absolute value. And then e to the negative 2kx dx. I can drop the absolute value on the exponent, but we get 2. Let's take out the b squared. And then let's just integrate e to the negative 2kx, which is simply e to the negative 2kx over negative 2k from a value from 0 to infinity. And we know that this takes value of, at infinity, we get e to the negative 2k x negative 2k times infinity, which just becomes 1 over e to the 2k infinity, which is just going to give us 1 over infinity, which is 0, and then minus the 0, so it's going to be minus 1 over negative 2k. So this, we can just make this plus, equals 1. So b squared over 2k equals 1, right? This 1 is the normalization condition. And at this point, we simply have to yeah, right, so we forgot to actually cancel these out, but we simply just do b squared equals k, because there was a 2 over here we forgot. those cancel, so it's just b squared equals k, and b equals square root of k, which we know that k, again, equals square root of 2, negative 2me over h bar, and we also know what e is. So yeah, we can just write that like that. I'm not gonna fully write out what k is, so I'm just gonna leave it as square root of k. Square root of k, e to the negative k absolute value x. Write it like that. So that's the final solution, normalized as well.